Let's see. Okay, so here is a small summary of what I talked about yesterday. So I essentially wanted to talk about semi-stability of sheaves on torsion-free reflexive sheaves on normal spaces, but normal projective varieties. I introduced these notions. And I just want to recall one of the central results, which I just mentioned, is the theorem of Mehta-Ramanathan or Flenner, which says that this is a nice notion because the restriction of an H semi-stable sheaf to a general member of a high enough multiple of an ample linear system stays semi-stable with respect to restricted polarization. And that's actually one of the pros of this semi-stability notion. I didn't go into the details, but I mean, so on curves, so historically on curves, there is only one sort of analogous notion of semi-stability, which is the slope stability. If you go to higher dimensions, you have more options. The other option maybe would be Giesecke semi-stability or the slope semi-stability, which I introduced and discussed here. And this, our notion has this property that it's good under restriction, whereas Giesecke is not. But then on the other hand, Giesecke has other advantages. Okay, so that's a central result. And then I discussed the Chern classes as sort of one number or class attached to holomorphic vector bundles, which try to measure, where we try to measure how non-trivial they are. And here is just a reminder of the definition. This was first defined for direct sums of line bundles, where you just write this this product of 1 plus the first Chern classes of these line bundles, and you expand and then order the terms according to degree. And then maybe because I didn't have so much time at the end of last lecture, I didn't do this example. Let me do an example here. Yeah. So to see how this works. So we are mostly interested in smooth projective surfaces. So there are only two Chern classes, namely C1 and C2, because C2 is in, as you can see here, it's in H 2 times 2, which is 4, which is the maximal degree. So if you take, for example, a V, which is the direct sum of 3 line bundles, then the C2 is computed like this. Yeah, so it's a sum of products and it's somehow symmetric. Yeah, if you think about this a little bit, this has to do with symmetric functions in the Chern classes of the individual direct summands. And so if you think in terms of differential geometry, this means it has to do with sums of products or symmetric functions in the eigenvalues of the curvature operator. So, and then, as I said, you can boost this to vector bundles which are not direct sums by the splitting principle, and then you get the definition. But just to get an idea, I did this example here. Okay, why did I introduce this? Mainly to have this this notion of a discriminant delta, which is in fact the C2 of the endomorphism of such a vector bundle. Yeah? So you have some rules how to compute with these Chern classes, and if you compute the endomorphism bundle, then of course, because it's V star tensor V, the C1 will be 0, and then the C2 will take this form, and I just note that the numbers appearing here are 2R and R minus 1. Yeah? So this is this will become important. You call this the discriminant. And why is this important? Because of this Bogomolov inequality, which in the simplest form maybe says that if you have a semi-stable vector bundle on a smooth surface, the discriminant of f is always bigger than or equal to 0. So as I said, this can be proved using algebraic geometry. And then there is a more precise statement that if the discriminant is 0, then the endomorphism bundle, which in this case has C1 equals 0 and delta, so C2 equals 0, is actually flat. Yeah, so we've seen that flat bundles are bundles which have C1 and C2 and all the other C's 0, but for semi-stable bundles, eventually you only have to look at C1 and C2 to check whether the endomorphism bundle is flat. Yeah, so examples show that this is wrong if the semi-stability condition is dropped. And at the very end, I gave this geometric example where I looked at this weighted projective space Y, or if you want, it's a cone of a degree 3 Veronese embedding of P2 inside P9, and then you compute the discriminant of the tangent of the bigger space restricted to a hyperplane section of some degree, and you see it's 0. Yeah, but this is not the endomorphism is not flat. I did not explain why this is true, and somehow the hint is that at the end of today's lecture, one can piece together the informations I will give you today to prove that this is not a flat bundle. Okay, so you should now see my slides saying this is chapter 3 on singularities, because as you see in this example which I gave and I just recalled, this has to do with singular spaces. Yeah, and so why are you interested in singularities? In geometry, for example, you want to take quotients by finite groups, which usually introduce finite quotient singularities because the action usually is not free. If you're interested in surface theory, for example, if you take a minimal surface of general type, say smooth, so this is a surface of general type without having -1 curves, you look at the canonical ring, which is this prod, which is this direct sum of sections in OX MKX. You take the proj, this will be a projective variety, but it will have singularities, and so they naturally appear if you think that the canonical ring can tell you something about the minimal surface of general type. Actually, you can do that in any dimension. If you take a variety of general type smooth, you can look at this canonical ring, it's finitely generated. You look at the proj, and you get a singular space with the singularities that I will discuss now. Yeah, so this is on the one hand of the classification general type, the other hand would be Fano's. So if you believe, okay, now it's a theorem, that the moduli spaces, compact moduli spaces of Fano manifolds, Fano varieties exist, you need to put singular spaces at the boundary, and also there, the right notions will be that of a KLT singularity, which I will introduce in a second. Yeah, and so all these singularity definitions, which I will discuss, they look at one object that you want to control, so that you have to impose conditions in order for this object to have the properties that you expect it to have. Yeah, so we've already encountered this omega x, which is the canonical sheaf, which is OX of the acanonical divisor. And so how do you control that? Well, you compare it to resolution. Yeah? So make the following definition. You take a normal variety, and the first condition you impose is that Kx is Q Cartier. Yeah? You want the canonical divisor to be Q Cartier to be able to pull it back and so on. And you assume that MKX is actually Cartier. Yeah, and then you take a resolution. Okay, I forgot to write that x tilde is smooth. So pi from x tilde to x by rational proper morphism, such that the exceptional set of pi has SNC support. So let me make a small sketch. Yeah. So the sketch is like this. You have your x. Some singularities, you resolve the singularities by x tilde and a proper birational map, and then you have this exceptional set here. Okay, I will come back to this sketch in a second. So now, if you have such a resolution, you want to compare MK or KX to KX tilde, so you take this multiple that is Cartier, and you pull it back. So you write MKX tilde in terms of the pullback, and since this exception set is exactly where the map is not an isomorphism, the additional, so the difference between mkx tilde and pi upper star mkx will be some devices supported on the exceptional set. Yeah? And then you make introduce some condition depending on the coefficients in front of exceptional prime devices. Yeah? So you call x terminal, or have x to have terminal singularities if all these numbers are positive. Yeah? Or a of e divided by m is positive, it's the same. You call it canonical if this number is bigger than or equal to 0. So at this point, it didn't matter whether I divided by m or not, but now it matters. You call this k Kawamata log terminal if this number is bigger than -1, and log canonical if it's bigger than or equal to -1. And then you get these four classes. Yeah? So let me explain what the meaning of this condition is. So the easiest is maybe canonical. So if you look at this equation, this means that if you take, say, m is 1, so you take a local section in kx, so a local n form, you pull it back to the resolution. A priori, it could have poles along the divisor, but this a of e being bigger than or equal to 0 means there are no poles actually. Yeah? So terminal means not just that there are no poles, but essentially that you have vanishing along the exceptional divisor. And then Kawamata log terminal is slightly more mysterious. You allow poles, yeah, so you no longer require this to be bigger than or equal to 0, but according to, I mean, these are weighted against the multiple you have to take, and then the ratio should be bigger than -1. Yeah, and so this definition, as I gave it into, has some choices, but this is actually independent of the resolution and the chosen multiple, as you can show. Yeah, and these are the singularities you have to deal with in all these three situations which I put on the left. Okay, so let's try to get some feeling by looking at examples. So what happens if I blow up a smooth point, yeah, in a point in a smooth manifold? Then the exceptional divisor is the Pn-1 if the dimension is n, and the discrepancy, okay, these a's are called discrepancies. This is equal to n-1, which is bigger than 0, since n is 2 or higher, so that you can blow up. So smooth points are as good as they get, they're terminal. Yeah, and in some sense, the definition of terminal is made so that you have singularities which are as close to smooth as possible. Yeah, so second example is if you take a finite group, subgroup in GLN, okay, without quasi-reflections, so that you don't produce smooth quotients, then the quotient has KLT singularities, so Kawamata log terminal singularities, and these are actually canonical, so even slightly better if the group is inside SLNC. Yeah, so you can imagine why this is the case. If you're inside SLNC, you preserve a volume form, and so this means downstairs you don't have to take a multiple of the canonical divisor to get it Cartier. Okay. Another set of examples is provided by cones, cone singularities. So let's take a cone over a smooth degree D hypersurface in Pn. And so let me again draw a picture here. So switch. So I will do this computation in the following picture. So I have my cone singularity. So this sits inside C n plus 1. I can resolve it by blowing up C n plus 1 in 0. And then I get a resolution. So let's see, how did I call this? I called this the x, and then okay, this is called x. Then I blow up Cn plus 1 in 0, and I get the proper transform of this divisor x inside the blow up at 0 of Cn plus 1. Yeah, so that's the situation. And so how am I going to compute these discrepancies? Well, I'm going to apply the junction formula twice, once down here for the divisor x inside Cn plus 1, and once upstairs for the divisor x tilde in the blow-up. Okay, let's do that. So this computation is carried out here. So by a junction, the canonical divisor of this hypersurface X, which is the cone, is this. Then I wrote, yeah, as you see, that I resolved this by blowing up the ambient space and then taking a proper transform, which is smooth. And then I used a junction again upstairs. But now a third point is that I know what how the canonical divisor of the blow up of Cn in a point, which is Cn tilde here, looks like. Yeah, it's just, okay, now we have this, okay, this should be Cn plus 1 here. Yeah. So this is just the pullback of the canonical divisor of Cn plus 1 plus n plus 1 minus 1, so plus n times the exceptional divisor, which is a Pn. Okay, that's just what I said. If I blow up a smooth point, I get a discrepancy dimension minus 1. In this case, it's n. And now I also know what this divisor, the strict transform is. Well, it's the pullback minus d times the exceptional divisor. Yeah, because if I pull back x, this has a default, so multiplicity d at the origin because it's a hypersurface of degree d. If I pull it back, I get the strict transform and then d times the exceptional divisor, which I can subtract to get it. And then I put everything together, and then this n and this minus d give this a, which is n minus d. Okay. Yeah, so what does this mean? It means that this x is terminal if d is less than n, it's canonical if d is less than or equal to n, and it's not canonical if d is less than or equal to n plus 1. So make this small observation that since the index, so this m, is 1 here, canonical and KLT are the same. So, and also we know that hypersurfaces are Fano as long as d is less than or equal to n. So KLT somehow corresponds to cones over Fano manifolds. So KLT is the local version of Fano. Okay, so let me just make the following remark. If n is bigger than or equal to 3 and d is less than or equal to n, so one of those Fanos, this gives non-quotient KLT singularities. Yeah, so you see, this gives dimension even n equal to bigger or equal to 2. So this gives, say, starting from dimension 3-dimensional singularities, you get families of these hypersurfaces, Fano surfaces downstairs, which so they deform to non-isomorphic singularities, whereas quotient singularities are rigid in dimension n bigger than or equal to 3. So certainly these singularities are not quotient singularities. Okay. So what are the general properties of this definition? So all these classes, so log canonical, KLT, canonical, terminal, these are stable under taking general hyperplane sections. Yeah, so if you take a projective variety that has this sort of singularities, you cut it with the general hyperplane, the hyperplane will have the same sort of singularities. There is another permanence property here. If you take which I haven't written, if you take a variety which has these sort of singularities, and you take a cover which is étale over the smooth locus, and you you have a normal variety which is of this form, it covers the smooth locus, and then maybe over the singular set it branches, then upstairs will have the same singularities as downstairs. Okay, so they go up. So if something is log terminal downstairs, it's log terminal upstairs. If the branching doesn't occur over the smooth part. Okay, so the good thing is that terminal singularities exist, but they don't exist in dimension 2. Yeah? So, and this together with point 1 leads to the fact that if you have terminal singularities, then the codimension of the singular set is bigger than or equal to 3. Yeah, and so this follows using a little bit of birational geometry of surfaces, namely the two basic and fundamental results. So if X is a normal surface, then you have a minimal resolution. What does that mean? You have a resolution X tilde to X that has no -1 curves in the fibers. Yeah, so you if you find such a -1 curve, which so it's a curve, an extensional prime divisor isomorphic to P1 with square -1, you can blow it down to a smooth point, to another smaller resolution, and so you can eventually find a minimal resolution. Yeah? And then if you have a resolution, the intersection matrix of the components is negative definite. Yeah? And so if you assume you have a terminal, a normal surface singularity, you go to this minimal resolution, and you use the fact that the intersection matrix is negative definite to see that you cannot fulfill this property that the discrepancy has to be bigger than or equal to 1. Yeah. Okay, so this means there are no actual terminal surface singularities, and then since this is stable under taking general hyperplane sections, if you take an n-dimensional variety, you cut down n-2 times to a surface. If the X was terminal, the surface is terminal, so it's smooth, but then you have a complete intersection surface in your X, which is smooth, which means that around your complete intersection surface, your variety has to be smooth. So there is another thing which is almost as easy to prove, but absolutely fundamental for what I'm going to talk about. Yeah? And so this, I mean, the younger people will not remember, and also I am too young to actually to have been around when this first came about. There is a famous conjecture, namely the Litman-Zariski conjecture, which tells you that if you have a normal variety X, and you assume that the tangent sheaf is locally free, then X should be smooth. And this has been proven in many situations, and I think morally the only open case is normal surface singularities, but it's open in general. But here, if I assume that I know from the start that X has KLT singularities, it's true. And okay, first this was proven using the deep theorem on the extension of differential forms, but there is an easier proof found by Druel, which I want to show. Yeah, so the statement is, you can detect whether a KLT space is smooth just by looking at the linearized space, which is the tangent sheaf. Yeah, so you look at the tangent sheaf, which a priori has less information, but in fact it has all the information you need for smoothness, where smoothness corresponds to freeness. Yeah, so being a vector bundle. Okay, assume the contrary for the proof. Assume that X is singular, then you construct or you refer to the existence of a special resolution, a so-called canonical resolution, so desingularization, which has exceptional divisor S and C, where the resolution is isomorphic over the singular set. So these two things together tell you that your space X is smooth if and only if you have an exceptional divisor. Yeah? So if it's smooth, you don't resolve at all, and if you resolve, there has to be some singularity. Okay, and then the main point is that this property, the third property, which says that every vector field, locally defined vector field on X, so a section of Tx, this lifts to a vector field on the resolution tangent, so it should be minus log E, tangent to the exceptional set of this resolution. Yeah, and this is somehow, you can prove this if you have a canonical resolution algorithm, this will lead to that. But you need a canonical algorithm where there are no choices, because otherwise you don't know, if you apply automorphism, that there is an induced map. Yeah, so, but this exists by, I don't know, Hironaka or the modern rework, sort of the modern reworkings of Hironaka's proof and the new proof of resolution. And so now you want to use your Tx locally free. Yeah, so the good thing is, if it's locally free, you can pull it back. Okay, you can pull back any sheaf, but that's not too dangerous if it's locally free. So you write the pullback of Tx. Okay, it's the pullback of this thing on the left. So, but then, since it's a pullback of a push forward, you have a natural evaluation morphism to the original thing, which is Ty minus log E. And this is a generic isomorphism outside of E. Now you take determinants, and that's actually, so you see, this looks innocent, but that's the place where you use the fact that Tx is locally free, so you can interchange determinants and pullbacks and all these things without creating trouble. So you take determinant, and then you get a map from the left to the determinant of the left to the determinant to the right. So you get a map from pi upper star of Ox minus Kx to Oy of minus Ky minus E. Okay, so this means that you have this subsheaf in minus Ky minus E, but now you take minus, yeah, so remember the discrepancy formula compares the pullback of Kx with the Ky upstairs, and you see that this forces all the A's to be smaller than or equal to minus 1. Yeah? So you see, this is because you have, for minus Kx is a subsheaf of minus Ky minus E. Yeah, so minus Kx sections here have to vanish at least once on, I think, on E. Yeah? Okay. Yeah, and so that goes the other way, and this means that the A's are smaller than or equal to minus 1, but they have to be bigger than minus 1. So that's a contradiction. So there cannot be any EI, so the space has to be smooth. Okay, that's very, very nice. And this is one of the cornerstones of the arguments that I'm going to run soon. Okay, so that's as far as proper sort of the introduction into KLT singularities is. And so I made the point that, I mean, the general KLT singularity is far worse in some sense than a quotient singularity. It's not quotient. But the mantra, which now appears in more and more places in this theory, is nevertheless these singularities behave as if they were quotient singularities. And I'm going to write one instance here. And this is topology. So I look at the local topology. So I take a point in my normal variety, and I look at the local fundamental group. So what is this? This is the limit over smaller and smaller open sets. So maybe I draw a picture again. The local fundamental group. How do you compute that? Well, okay, it's always the same picture. You see, singular space. It's not necessarily isolated singularity, but that's easier to draw. So I take smaller and smaller neighborhoods in the Euclidean topology, but I always take out the singular point. So even though this might not be an isolated singularity, I just take out this point, and this limit then I take the pi1 of this u minus the point, and this has a limit. So you can compute this as follows. You take a sphere around this singular point, and then if it's small enough, this has some pi 1. You intersect it with the singular set, it has some pi 1, and that's the local fundamental group. So it's really somehow the topology, the fundamental group, that is hiding in the singular point. And we call this the local fundamental group. Yeah, and in which sense are these KLT singularities like quotient singularities? Well, because of the following result of Chu, if X is KLT, there exists a finite group G together with a homomorphism of groups from this local fundamental group to this finite group, such that the representation theory of the local fundamental group is the representation theory of G, which means that every representation of the local fundamental group factors through this finite group. It's pulled back from, from G via P. So this is not true if you leave the world of KLT singularities and look at log canonical singularities. If you look at the cone over elliptic curve, this does not have finite fundamental group at 0 and also not this property. I want to point out that now we have a much stronger result by Lukas Braun, who's now in Freiburg, that says that every KLT singularity actually has finite local fundamental group, but we will not need this for our arguments. And let me point out that in dimension 2, quotient singularities are the same as KLT singularities. So every KLT singularity is quotient in dimension 2. Okay. So this is a result of Chu, which at first doesn't look too useful because it's a result about a singular space which might have singularities along curves, surfaces, and so on if the dimension is high, and you just remove one point. But starting from this with an induction using Whitney stratifications, we can obtain the following result by myself, Kebekus, and Peternel. It says that we can eliminate the difference of fundamental groups, at least from the representation theory side, between a singular variety and its smooth locus. Yeah? So if you take a projective variety with KLT singularities, then you have a finite Galois map from X hat to X, unramified over the smooth part, so which we call, this is what we call quasi-étal, such that every representation, so up here the difference has vanished, every representation of the fundamental group of the regular part upstairs factors through the representation of the fundamental group of the whole space. Or in other words, every representation of the fundamental group of the of X hat reg can be extended to a representation of the fundamental group or factors through this phi 1 of X hat. Okay, let me quickly close the window. So. Okay, yeah. So what does it have to do with vector bundles? Well, you get the following corollary. In the set of notation of this theorem, take a flat vector bundle on X reg, so on the regular locus downstairs. Then, if I pull this this back, I get a flat vector bundle on the pre-image of the regular locus of X inside X hat. This extends to a flat vector bundle on the whole of X hat. And how do you do that? Well, as I said, because this map gamma is étal, unramified over the regular locus, you know that the pre-image of X reg is contained in the regular locus of the variety upstairs. The complement here has codimension bigger than or equal to 2. And so the fundamental groups of this pre-image and the fundamental group of this regular locus of X hat is the same, because they're both smooth and they have, one is an open subset in the other with complement of codimension bigger than or equal to 2, then you have this a natural map from the fundamental group of the pre-image to the fundamental group of XVec. This is just push forward, and then you have this representation defining the flat vector bundle V from the regular pi1 of the regular locus of X to GLR, which is the rank of the bundle. And so you compose these maps, so you get a homomorphism from pi1 of X hat reg to GLRC, and now the theorem tells you that exactly that's what you have. This representation factors over pi1 X hat. And so then you write down the flat vector bundle on X hat using this representation, which is the dashed arrow, and then by functoriality, this is just the restriction of this vector bundle to the open set, which is in the pre-image, is the one that you already had. Yeah, so this is how this works. Yeah, you can extend, after discover, you can extend representations, and so this means flat vector bundles extend over the singular locus. Okay. So I'm going to use this topological result to derive a flatness criterion for sheaves on KLT spaces. Yeah, and for this I want to recall the Bogomolov or the strong version of the theorem of Bogomolov on the discriminant, namely, yeah, I had it on the summary page, which I showed at the beginning of this second lecture. So I take an H semi-stable vector bundle on a smooth projective surface, and I point out that I have two regularity assumptions here. Namely, I'm looking at vector bundles only, so locally free sheaves, and I'm on a smooth surface. Yeah, so if the discriminant of f is 0, then the claim or the theorem is that the endomorphism bundle is flat. And so the question is, what about reflexive sheaves on singular spaces? And so why am I interested in this? I'm interested in this because I look at potentially singular varieties coming from any of these motivations, like quotient singularities, canonical models of varieties of general type, Fano varieties occurring at the boundary of the moduli space of K semi-stable Fanos. Yeah. So, and that's my situation. And if I have these singularities, in the first lecture I showed or I explained that natural reflexive sheaves are the ones where I take a geometric sheaf on the regular locus, like the tangent sheaf, the cotangent sheaf, omega p, or some combination, some tensor sheaf, and I push them forward to the whole space. And I want to know what's happening with respect to this map, this theorem. Okay, so for this, I first have to make sense of this discriminant. However, I already set the theme in the first lecture when I defined semi-stability, which essentially depends on first Schoen class and intersection of the first Schoen class with some divisor, that, okay, you go to a high degree complete intersection, in that case curve, and you compute there, and you are going to do the same here. Yeah, so my geometrically motivated sheaf theoretic setup is the following. I take a projective variety with terminal singularities. So I will explain later. And let's restrict to this case first, yeah? And not KLT, but terminal. And I explained, or at least said, that this means that the codimension of the singular set is at least 3. And then I take a locally free sheaf on the regular locus and then push it forward so I get a reflexive sheaf. Yeah, that's usually how our sheaves arise. So now I want to define C2. Well, C2 is a class in, should be a class in H4, so I should be able to intersect it with n-2 copies of an ample divisor. So I define this number, which I call C2 of f times h to the n-2 for an ample x, by the same trick. Yeah? I go to a multiple MH, which is very ample, so it's a lot of sections. I take this time n-2 general members of this very ample linear system. I intersect them because my singularities are in codimension 3. This will give me a smooth surface inside the regular locus of x. So the picture is exactly the same as for curves that I did C1. And then I restrict my sheaf F, which was locally free on the regular part, to the smooth surface. It's a vector bundle on a smooth surface. And so I know how to do C2. I compute C2, and then I have to divide down by 1 over m to the n-2 because of the fact that I had to go to this multiple mh in order to have these sections. Yeah, of course, again, this is just the most down-to-earth way of defining this so that you have some feeling. Proving functoriality properties with this is hard, and so this is just a remark. There are other, more invariant ways to define this. In particular, the definition does not depend on M and S as before. And the other remark is that this terminal singularity restriction is just for this lecture series. You can do it if X is just KLT, because then if you do this construction, you cut down to a surface. This will no longer be smooth, but it's a KLT surface singularity, so it's a quotient singularity, and you can work with orbifold Chern numbers. Yeah, but I want to avoid this because it does not add any more philosophical meaning. It's just technically more demanding. Okay, similarly, so once I have C2, I can do the same with C1 squared and other classes of degree 4. So I can define delta of f times h to the n-2 now. Okay, and what is the main theorem whose proof I want to explain in the last 15 minutes? I have the following flatness result, which is a sample flatness result to be used in the third lecture, which just extends this the strong form of Bogomolov theorem to this setup. So let X be a projective variety with terminal singularities, and then I take a sheaf, a reflexive sheaf, which is push forward from the smooth locus as above. So push forward of a locally free from the smooth locus. I make the same two assumptions. FH semi-stable for an ample divisor, and delta of f times h to the n-2, which is this number just defined using the C2, which is 0. Then, if my space X is the same as this X hat, which I produced using, so this is the global version of this result of Chu. Let me go back. This is the last result I explained. Yeah, for every X, there is this X hat, which has this property that the fundamental groups are almost the same, at least as far as representations are concerned. So on this maximally quasi-étale cover, that is our name, this endomorphism sheaf is flat. In particular, it's locally free. Yeah? So a flat vector bundle in particular is a vector bundle. Yeah? And you see here, I take a reflexive sheaves. So usually end F, it's just reflexive. But this theorem contains a statement about a sheaf being locally free. And this is usually the first step in any argument that uses this result, is to use the fact that the sheaf is not just reflexive, but locally free. Okay. So I'm going to give the proof. And in the proof, we're going to use the following basic results on flat vector bundles, which in fact has nothing to do with flatness, but just with boundedness. Yeah, so as you can imagine, I want to cut down to surfaces and then prove something there, and then use the fact that, okay, that you all know, if you have two, say vector bundles on a projective variety, if you restrict them to a high enough a hypersurface of high enough degree, because of Serre vanishing, if they are isomorphic there, you can lift this isomorphism to an isomorphism on the whole variety. Yeah? But now here I have to use this for a lot of sheaves at the same time. So the statement is, if X is a normal projective variety and E is a reflexive sheaf, which I'm starting from the beginning. Yeah, I have this from the beginning. Then for every R, for let's say R, maybe not the right formulation. For R, the rank of E, there exists a number M such that for general elements D1 up to Dn minus 2 in K times M times D, where K is again bigger than or equal to 1. So essentially I prove something for MD and then all positive multiples of MD. And the corresponding complete intersection surface, the following holds. If F is any flat sheaf of rank R on X, then F is isomorphic to E if and only if F restricted to S is isomorphic to E restricted to S. So this is important, that I have this statement for all flat sheaves of rank R at the same time. And so this has to do with the fact that flat sheaves of rank R on X form a bounded family. So I can do Serre vanishing for one member, and then it holds in the neighborhood of the bounded family, and then after increasing the power M here finitely many times, I can do it for all members of the bounded family at once. Okay, let's assume that. So this allows us to cut down to the surface situation. So I'm now going to prove this theorem. Yeah, so I have an H semi-stable sheaf, a vanishing discriminant in this sense, and I assume that my space has this property that flat sheaves extend from the smooth part to X, and I'm going to prove that this endomorphism is flat. Okay, so first I have to find a representation. Yeah, so for this I apply the previous proposition about surfaces. 2E equal to end of F and R the rank, together with the theorem of Meta-Ramanathan and Flanner, to find a surface with the following properties. Okay, first, S is complete intersection surface. It's smooth. It's inside the regular locus. Then that's Meta-Ramanathan for the sheaf F. F restricted to S is semi-stable. Oh, that's okay. And then the difficult part is taken over by this proposition. For any flat vector bundle G of rank R on X, G is isomorphic to E, if and only if G restricted to S is isomorphic to E restricted to S. And so you see, I'm working towards showing that E is flat, but I don't know a priori what is the representation that will occur. And so I have to deal with all the potential representations at once, and that is what the proposition does. Okay, so now I have reached my regularity assumptions, namely, S is a smooth surface, the restriction of F to S, because F was pushed forward to X from the regular locus of a locally free sheaf, is a vector bundle on S and it's semi-stable. Moreover, by definition, well, remember how I computed or how I defined this discriminant delta F times H to the n minus 2. This was by restriction to surfaces. This means that the delta of F restricted to S is 0 by assumption. Okay, so I apply the traditional, the classic result, which means that the endomorphism sheaf of f restricted to S is flat. Yeah, but because everything is nice and smooth and locally free, the endomorphism sheaf of f restricted to S is the restriction of the endomorphism sheaf. Yeah, so these two operations, restriction and taking endomorphisms, they commute in my setup. And so this is given, the restriction is given by a representation, rho S, on the surface, pi1 of S to GLR of C. Okay, so this means that E restricted to S is a flat sheaf G coming from this representation rho S. Yeah? So now you think you're done, yeah? Because you remember the smooth in the smooth setup you have Lefschetz theorem. Yeah? So you take a smooth projective variety of dimension at least 3. You take a hyperplane section, the surface, or something which is at least the surface, and then the inclusion from the hyperplane into the whole variety induces an isomorphism on fundamental groups. But now my X is singular. And then the Lefschetz type theorems just tell you, so these were, for example, proven by Hamm long time ago, that this surface has only the same fundamental group as the regular locus. Yeah, so just, okay, everyone sees this picture in front of him or her, but let me draw this. Yeah, so this situation in general is like that. If you take X and you have some singularities, so they're in codimension 3 in our case, then I take this hyperplane section or repeated hyperplane section, which gives this surface S, which sits in the regular locus. Then the fundamental group pi1 of S is not necessarily the fundamental group of X, but it's just the fundamental group of the smooth locus. And there now you see why we had to deal with the difference of pi1 of X reg and pi1 of X. Yeah, so this is what Lefschetz theorem tells you. And in general, this is really the only thing you can prove. Okay, so let's go back. Yeah, so Lefschetz type theorems tell you that you can extend somehow this representation to a representation of pi1 X reg. So if you have this representation, you produce a flat vector bundle. Yeah, so you get rho 0, okay, this representation, and so you attach this this flat vector bundle. Maybe I recall how this is done. Yeah, so I used this several times already in this second lecture. But yeah, so if I have a representation rho from pi1, let's say in this case X reg, to GLR, then I look at X reg tilde, the universal cover, times C to the R, and then I act with this representation rho on the right and the deck transformation action of the fundamental group on the left, and I take the quotient, which is denoted by this, and this is a vector bundle over X, the original space, X reg. So this is G of rho. Say rho 0. Yeah. Okay, I have this flat sheaf, this flat vector bundle on the regular locus, but now I use the fact, which is my last assumption in theorem, that I'm on this space where I can extend flat vector bundles over the singularities. Yeah? So as X is maximally quasi-étale, which means that it's equal to this X hat, this representation, or equivalently this flat vector bundle, extends to a flat vector bundle on the whole of S. And now, since everything here is functorial, so this passage from the vector bundle to, from the representation to the vector bundle, since I started with this representation of pi1 of S, and if I take this G rho, which I now I have this representation on the whole space, and I was attached the vector bundle, I restrict it down to the surface I started with, so from which I extended the representation. I find the vector bundle, the flat vector bundle on the surface, which comes from the representation rho s, but that was E restricted to S. Yeah, so now this means that I have a flat vector bundle on X whose restriction to S coincides with E. But then I use this, this third property of my surface S, namely, since the two restrictions are isomorphic, the original sheaves are isomorphic. So this means this and F, which is E, is isomorphic to this flat vector bundle, so it's a flat vector bundle. So in particular, it's locally free. Yeah, and so you see, while I have not a complete extension of the result of so this strong form of Bogomolov to my singular setup, I have something which, as you will see, is as useful. Yeah, so I recall what I just proved in this lecture is that if I have this projective variety with terminal singularities, for which we've seen examples, for example, isolated singularities which are cones over degree d hypersurfaces in Pn, where the d is less than n, for example, degree 3 hypersurface in degree 3 hypersurface in P5. Yeah? And then I have this reflexive sheaf, which is semi-stable and has vanishing discriminant. Then the endomorphism is flat on the maximally quasi-type cover. Okay, I think I stop here because this is a nice point to go on a break, because this is essentially everything I'm going to say about sheaves. And in the third lecture, I'm going to move on to apply this sheaf theory to do actual geometry. So thanks a lot for your attention, and please ask questions if you have some comments. Are welcome. Yeah, thanks.
So, Daniel.
Any questions?
Daniel, out of curiosity, how do you prove this Bogomolov thing? I mean, I seem to remember there was one proof which was using Hermitian-Young-Mills, which says that you have a Hermitian-Young-Mills metric, and then if C1, C2 is equal to 0.
Yes, so on the surface, for the polystable case, that's what you do. So you see, that's somehow the philosophy. I would not say it's hopeless, but it's definitely daunting to try to do the necessary analysis which you do on the smooth surface for vector bundle to extend that to a reflexive sheaf on a normal space. Yeah, so I mean, what has been done is that there is this famous paper of Bando and Siu,
Right.
where they do deal with reflexive sheaves on smooth spaces. Yeah, and so that's the polystable case, where you also see how the vanishing discriminant then leads to the fact that you have to be locally free immediately almost. Yeah? Because singularities of the sheaf would contribute C2. Yeah, but I mean here, this is somehow mixed. You see, you have two singulars. You have the singularities of the sheaf on a singular space. And the interesting piece where everything happens is exactly where both collide. And in the end, I'm not going to work on a smooth space. I'm going to work on a singular space, and you would have to separate these two singularities and see what comes from the sheaf and what comes from the space, and then say the sheaf is locally free on the singular space. Yeah, so the answer is the method I present here pushes the analysis to the smooth surface.
Okay.
And everything else is just topology.
Okay. But in general, there was no progress in analysis since Bando and Siu, right? So there is no...
On the smooth space, there is no, I mean, on the normal space, I mean, maybe Henri can comment, but the main focus is Keller-Einstein, but I think Hermitian Young-Mills on a normal projective variety, I'm not aware.
Yeah, as far as I know, I don't think anybody has really ventured into that.
Okay. So in any case, there's certainly nothing which we can just use, right? So it's
No.
okay.
I mean, somehow the message here is that for this theory, because it's only C1 and C2, and I mean, you see, once you have this on the surface somehow, I mean, this theorem that you only looked at C1 and C2, then it's a surface theory. You can produce the representation on the surface, and then the question is purely topological in some sense, or representation theory of pi1s, whether you can go back up to the whole variety.
Okay.
And that's true.
Right. Okay, thank you.
Yeah, and can I ask technical questions about the isomorphism of the sheaves restricted to the surface?
Yes.
Yeah.
Maybe
So first question: the surface should be taken from the family? Yeah. So you always think of the surface varying in the family. Yeah. So you cannot take, of course, a specific surface.
Well, no, I have this result that, okay, I mean, maybe it's not the, I mean, so that if I fix the dimension and I have x, and I fix the rank of the flat sheaves I want to look at. Yeah, because this is determined a priori by the fact that I want to show that a certain vector reflexive sheaf of a certain rank is flat, so the rank is fixed. And then you see, my surface only has to be good in some sense with respect to the fixed with respect to the fixed sheaf E. Because
so it doesn't depend on F, yeah?
No, that's the point. So you essentially the only thing you have to do it has to be Mechta-Ramanathan for E. And then you have to go high enough in your multiple to have enough vanishing to have this lifting, but that is just a matter of the multiple.
Yeah, and I have another question. So how to compare F and E? You should produce some map from F to E or vice versa in order to see vanishing of the kernel and co-kernel, yeah, after the just twist, probably.
No, I mean, you just you look at the Hom sheaves, and okay, essentially the boundedness of the family of flat sheaves gives you boundedness for the Hom sheaves, and then you just lift Homs.
Yeah. So you lift all of them. I see.
I say lift all of them, and then there is some lift, and then the restriction is not. I mean, there is a little bit, yeah. The restriction is an isomorphism, so I mean, you have to discuss a little bit why this has an inverse, or I mean, you have the two morphisms and they are inverse to each other on the surface and so on, but that's not so much of a problem once you have them.
Yeah. I just was asking about general arguments.
No, I just wanted to point this out because, of course, I mean, in most other talks, you would ignore that and you say, yeah, look, you restrict to this meta-Ramanathan surface, you produce the representation, then you produce these other sheaves, and then you know they are on this high degree surface, they are isomorphic, and then you say, yeah, then they have to be isomorphic. Yeah, but you cannot change the multiple in the surface after you chose it once. Yeah, I mean, you produce the representation from a specific surface, you cannot go to more multiples after that. And that's somehow the point that we first have to use this boundedness result to fix the multiple before you restrict and produce the representation.
Yeah, I see. Mm-hmm.
It's a subtle, well, I don't know whether it's subtle point, but of course, this is not how you first came about with this proof. You do this heuristic, you restrict and so on, and then you are scared because you forgot to. You have this representation, and you want to say that you can restrict to that surface, And then you see only, oh, I don't even know whether this Serre vanishing holds for the specific flat bundle which are produced from that representation. So you have to organize yourself before starting this restriction business.
And about your result with Galois cover, how of the year 16th, yeah, so how complicated, yeah, with this one, yeah, so how complicated is the proof? Just
so I think the point, I mean, the main point is that you have to organize yourself along witness stratifications of the singular set, of the variety and hence of the singular set. So essentially, you see, I mean, if you have one singularity stratum, then the rest is somehow a cone over that. And so this says something about the topology of some hypersurface sections transversal to the singularity set, that somehow it's like a local system. Yeah, so there somehow the topology, if you have, for example, a map which is unbranched at one point of a generic point of a singularity stratum, then it has to be unbranched along the whole stratum. I mean, I would say standard techniques, but you have to be very careful how to organize yourself.
Okay.
Yeah. So I mean, witness stratification plus the local pointwise result.
Okay. Thank you very much.
Sure.
Thank you, Maya. Right, thank you.